In section 3.2, we're going to talk about the derivative a little bit more as a function. Honestly, if you noticed what I was writing at the end of last class when we were talking about this example together, you noticed there's this idea of a function already. Like, for example, we looked at where the maximum occurred. We looked and say, oh, the maximum occurred at 3. So what we noticed is that f prime of 3 is equal to 0. And remember, this little prime right here means that we're looking at the derivative at a point, in this case, the derivative at 3. And remember, the derivative is another phrase that we use to discuss the slope of the tangent line or the slope of the curve. So those are all synonymous. So in 3.2, we're going to talk about the derivative as a function a little bit more. Really just kind of get the hang of the notation and the different types that we'll run into. Different ones have different pros and cons, so we want to make sure that we have those in mind. So with that being said, let's go ahead and just kind of read what this says. Previously, we discussed the derivative at a point. And again, that at a point is going to be basically the input to the function that we're going to be looking at here. Now we have to investigate the derivative as a function derived from f by considering the limit at each point x in the domain of f. So the derivative of a function f of x with respect to a variable x, and we'll discuss this idea of with respect to more as we go, is the function f prime whose value at x is defined as follows. So again, here's this f prime notation. F prime of x is just the limit of the difference quotient as h approaches 0. So the limit as h approaches 0 of f of x plus h minus f of x divided by h. So this is the formal definition of the derivative. Should we ever need to understand what it is? It's just a tangent line, and we see that tangent line coming from the limit of the difference quotient. So talking a little bit more about this phrase with respect to variable x, recall that x is the independent variable and y is the dependent variable. So this is what we consider in our most general form, but again, we'll also consider other scenarios where we'll consider like time is the independent variable and position. So we have like time t and position s. We'll also consider those as other scenarios when we look at the derivative is more in its physics applications. We also may run into scenarios involving like theta, where, for example, like we'll have some sort of angle. Theta and the output is typically just going to be some typically S or Y is used as well, but we'll just use, oh wait, hold on. I have this in the wrong spot. So the angle would be, theta would be your independent variable, and typically it's going to be associated with some sort of output, which is typically also Y in that case. So again, these are the different independent variables we'll run into in different scenarios. Today we're mostly focused on x, but we'll see a couple other examples. The domain of f prime is the set of points in the domain of the original function f for which the limit exists, which means that the domain may either be the same or smaller than the original domain. So the derivatives domain, thinking about the derivative as a function, will either have the same domain or something that's smaller. Nothing is picked up by taking the derivative or finding a derivative. So if these are just kind of some logistics, if f prime exists at a particular x, we say that f is differentiable at x. That is to say, we can plug x into the derivative. If f prime exists at every point in the domain, that's when we call the derivative, or excuse me, that's when we call the function differentiable. And we'll consider these ideas of the graph graphically here more in the second part of 3.2 on Monday. What we're going to the part we're going to focus on in 3.2 are these ideas down here. Maybe draw a line here just to separate it. We're going to talk mostly today about the notation. And notation. Is that spelled right? Notation? Did I notate that correctly? Okay. So some common notations, I could just read ahead, for the derivative of a function y are as follows. So you can see right here, we have f prime of x, or y prime. This is the prime notation. And if you remember back to the first day, one of the inventors of calculus, Newton's the most commonly one, but there was another guy with the last name that began with L. Does anyone remember what the guy's last name was? Leibniz, yeah. So Leibniz. So this is the notation that he would typically use. And then this notation right here, these show up a little bit more in the physics calculations. So these are a little bit more Newtonian. But these mean the same thing. So whether we're talking about using our prime notation or we're using this sort of differential notation, they are all equivalent in what they're telling us to do. This one is saying, let's go ahead and find the derivative of f of x. And of course, remember, f of x is the same as y. So this is y prime. So let's see. Maybe just how to read this right here. There's a lot going on. This is read as the derivative of y with respect to x, or I'll just say dy dx. But one thing to note about this x right down here in the denominator, this right here is going to be your variable. More specifically, it's the independent variable. So that may change when we're talking about, or it will change when we're talking about time to t. We're talking about angles. That'll be d theta in the denominator. So that is all. That's this denominator of this notation will tell you what the variable is. So keep that in mind. We'll see various examples. Down here, the derivative of a function at a specified number x. So let's say, so a is just going to be some number. So a is just some number, some real number, we should say. We won't really deal with complex numbers in this course. So this notation right here, all of these are equivalent. This one probably makes the most sense. This just says plug a into the derivative. This is the scenario where you'll consider the differential notation. So this vertical bar just says that the derivative is going to be a function, and you'll plug into that derivative the number a. So, and again, this is just saying, you know what, y and f are the same thing. And this is just saying, you know what, this is just kind of more indicating the variable. So you can see right there, there's the x, it matches as your variable, as the input. So again, this vertical bar with this little x equal a at the bottom is just saying, let me write it, plug a, so I'll just specify what is a, number a into the derivative. So that's what that is saying. For those of you going on Calc 2, you'll end up using this differential notation a lot with that vertical bar. We're going to use it regularly at the end in Chapter 5, but especially those going Calc 2, that typically is the preferred notation. It just helps you keep track of your variables a little bit better, and especially for those going to Calc 3, when you're in multidimensional calculus or vector calculus, you'll end up using this notation more or less all the time. Okay, so that's the notation. Let's make sure we know how to use it. So we're, in this next example, asked to calculate the derivative of the function and then find the value at the specified. So here is our function. So what we're going to do, I'm going to go ahead and find the derivative. F prime of x is equal to the limit as x approaches, as h approaches 0 of 4 minus x plus h squared minus x squared, all divided by h. So f of x, so it would be 4 minus x squared. There we go. So if you go through this computation, you're going to end up with minus 2x. Yes, I did do that in my head. And that's why I want to go ahead and get to the shortcuts before we leave class today. So this is how we found the derivative last class. There's a series of steps. When all is said and done here, you're going to get minus 2x. There is a shortcut, which we will talk before we get to the weekend. I will teach that so you can use it in your homework. So what we have right here, just to maybe shorten it, we found that f prime of x is equal to minus 2x. And what we're asked to do here is find f prime of minus 3. What this means is plug in negative 3 into the derivative. So f prime of minus 3 is going to be minus 2 times minus 3, which is positive 6. Does this make sense? And what do I mean by that? Consider the graph over here. At negative 3, we're looking at this point on the graph. So again, this is where x is equal to minus 3. That point on the graph right here, is it increasing or decreasing over there? It's increasing, so what do we expect our derivative at negative 3 to be? And indeed it is. So again, this 6, if we were to go ahead and draw the tangent line, so this right here is the tangent line, this has a slope of 6, which we got by plugging negative 3 into the derivative. So let's consider the second scenario, f prime of 0. Before we even plug it in, you should go ahead and just say, okay, this is where I'm at the graph. What is the slope of the tangent line right here at the vertex? 0 is a maximum. So the tangent line right here is going to be horizontal, so m is equal to 0, which is consistent with what you get when you plug in 0. On the last scenario, f prime of 1 is, we're going to expect it to be negative, because you can see right here where I put a point in purple. And, well, what is its value? Negative 2. So the derivative as a function, functions take input. That input is going to be the slope of the graph at wherever the input is. Any questions on this example? All right, so let's slide down here and look at the other notation. So again, here we're considering an example relating s and t. So just to kind of make sure that you're comfortable with what it is in relation to what we have above, you could think about this as f of t is equal to the square root of t. This first problem is asking us to find f prime of 1. This second is asking us to find f prime of 2. And the third one is asking us to find f prime of 4. But you can see we're just using this notation involving differentials, where we have, this is telling us, find the derivative of the function s with respect to t, and then plug in t equal to 1. So you're going to start running into so like if we were to kind of take this ds dt, does everyone agree that s is just going to be the square root of t? So what you may also see written is this is equal to the derivative with respect to t of the function square root of t. So notice the only thing that happened is we made the substitution for s, and then we have the square root of t over there on the side. So this right here is basically indicating that what I'm going to do is take the derivative of the square root of t. Which, by the way, something to start dropping in your mind, is the same thing as taking the derivative of x to the 1/2. Remember that the square root of t, not x, it should be t to the 1/2, excuse me. The square root of t is the same thing as t to the 1/2. So, to find the derivative, you can go through that big long formula, or the 1/2 will go here, and then we'll have t to the minus 1/2. And to switch it back to positive exponents, this is 1 over 2 square root of t. So this right here, just to maybe shorten things up, the derivative of s with respect to t is 1 over 2 square root of t. I just rewrote that without the intermediate steps. So the takeaway from this little example is just understanding what this notation is. S is some function in terms of t. So this right here, when we have dt, d over dt, and then the square root of t next to it means take the derivative of this guy, and you can see that's what we get down here at the end. Any questions on this, what anything I've written up here means so far? Okay, so now let's go ahead and actually find the values. So this first one, I already used red, let me change it to blue. So we have ds dt evaluated at t equal to 1. Well, this is going to be 1 over 2 square root of 1, which is 1/2. Any questions on that first one? Then let me pose this question. What is this 1/2? Just make sure we're still holding on that, Destiny. It's the slope of the tangent line at t equal to 1. So you can see if I were to draw a tangent line right here, it would have a slope of 1/2. So again, just keep in mind what these numbers represent, and that'll really help you when we get into some of the more word problems and the application problems at the later part of chapter 3, chapter 4. So we have two other examples right here. ds dt evaluated at t equal to 2. And we also have the ds dt evaluated at t equal to 4. Go ahead and do those really quick while I take attendance. So ds dt evaluated at t equal to 2 would be 1 over 2 square root of 2. Remember that typically at this point, as you see examples, the denominator will always be rationalized. So you'll have multiply top and bottom by the square root of 2. So you get square root of 2 over 2 times 2, or square root of 2 over 4. That's typically what you'll see when it comes to if it's a multiple choice example, or as you see the viewing examples. I don't think the homework, like entering, gets picky, but realize that you'll typically see radicals out of the denominator. Then the other scenario is that you'll have ds dt evaluated at t equal to 4, which is going to be 1 over 2 rad 2, or 1/4. Here we are continuing in section 3.2. Remember that section 3.2 is understanding the derivative as a function. So we understood it last week in terms of like, okay, it's a function, you can plug something into, what is this input, what is this output? The second part of section 3.2 is concerned with making sure we understand the graph of the derivative. So we're going to do a few kind of look at what's happening, and then we're going to go ahead and maybe just look at a variety of examples just to go ahead and make sure we understand each scenario. One thing to keep in mind is the idea, if you look at, let's go ahead and just maybe look at this part right here. If we were to look at B, this point in the blue graph up here represents the original function. If we look at the blue graph at B, it is decreasing. And because the graph is decreasing, what do we know about the slope of the graph or the slope of the tangent line? It is negative. So you can see right up here, this is the original function. Where down here in red, we have the graph of the derivative. So down here, we have the graph of the derivative. And if we look at derivative, gotta spell. So if we looked at that point that I just called out, right here at B, notice that in the graph of the derivative, that we have the same x value. So you can see the x value here is 5. This graph is lined up. Actually not 5. I guess it's about closer to like 3 right here. So you can see right here when we look at the graph of the derivative, notice it's in the fourth quadrant. That is to say, because the slope was negative here, this point, the corresponding point on the graph of the derivative, is going to be in the fourth quadrant. So what we're looking at in terms of the axis is, let's look at the vertical axis. Notice that in the original, that this represents the y values. The vertical axis represents the y values of the function, the outputs. But if you look at the derivative, notice that the derivative, the vertical axis, represents the slope of the original function. So if we look at, let's look at point D, notice at point D we have a minimum of the graph. And when we have a minimum of the graph, again you can see it right there, what was the slope of, or the slope of the tangent line or the slope of the function? When we have a minimum, the slope is? It is going to be 0. So you can see we have a minimum right here. So if you were to draw the tangent line, it has a slope of 0. Notice that at D, what we end up with is the x-intercepts. So maybe just calling that out there specifically in terms of a statement up here. Let's go ahead and, this is kind of helpful. Notice that when we have a max or min, this means that the slope is 0, which means we have an x-intercept on the graph of the derivative. So that's going to be a nice thing to hold on to. So we've seen two scenarios. Where the slope is negative, that's when the corresponding graph for the derivative will be in a negative quadrant, either 3 or 4. When the slope is 0, that's when the graph of the derivative is going to have an x-intercept. And then lastly, consider point E. You can see point E right here. The graph is increasing. Because the graph is increasing, what do we know about the slope of the graph? It is positive. You can see that right here. And because the slope is positive, that means that corresponding point on the derivatives graph, it's going to be in a positive quadrant, either 1 or 2, depending on where you are on your x-axis. So really, that's the basic idea. It's just now kind of looking at the graph, figuring out where it's increasing, decreasing, or where it's max or mins, and then just go ahead and consider the graphs of the derivative. So let's go ahead and maybe look at a few examples right here. I hope the internet's working well enough to do this. If not, we'll go ahead and try it out right here. So over here on the left side of the screen, I'm going to have to step away with the iPad because this is just a website. You can see it linked at the bottom of the page. If you look at the graph right here in blue, this is going to be the original function. And this is a quick little multiple choice test. We have 3 options right here. which one is going to be the graph of the derivative? Let me go ahead and just give you everyone a moment to look. And then when you think you have the answer, go ahead and hold up either 1, 2, or 3 based off of what you think. So here's the original function, 1, 2, or 3. Which one is the graph of the derivative? Let me give you maybe 15 seconds to process. Then I'll go ahead and reason through these first few together. If you think you know, just go ahead and put them. Okay? There's no grade attached to this one, so feel free to guess.
I should write it.
So, I see a lot of 2s. If we look at this one, I'm going to go ahead and just provide the reasoning for the first one. I'm looking for max and min. So you can see right here at -4 is a minimum value. So that's where I'm going to expect a x-intercept to be. So that allows me to eliminate 1 right away. Because again, this is a minimum and you can see there's no x-intercept there. Then the next thing I'm looking at is this part is decreasing. So because this part before -4 is decreasing, I'm expecting this graph of the derivative to be in the second in a negative quadrant. So you can see right here, this is a positive quadrant, these are negative quadrants. So for those of you who said 2, that is correct. Very good. Let's go ahead and do maybe 1 or 2 more of these, because the ideas from this one will show up in the section 3.4. So very good. Let's go ahead and reset the graphs. Now let's take a look at this one. Let me go ahead and give you another 10, 15 seconds, and when you think you know the answer, just hold up 1, 2, or 3. Okay. Okay. I see a couple 1s and I see a couple 3s. So let's check 2 to make sure it's not 2. Good. No, I didn't see any 2s, so no, this is not correct. So again, let me just go through the reason again. I'm going to look for the max or mins. I see there's a max right here at -6. So I expect in this case, it's about -6. It's a little bit off. So it's about -5.5. I'm expecting an x-intercept. So that means I could immediately throw this one out. 3 is out. And the reason 2 is out is because if you look at this, before -6, the graph is increasing. So I expect to be in a positive quadrant. So you can see up there at 1, that is correct. And you can go through and do a couple more reasonings. In the case of the right here about -0.5, it is a minimum. And you can see right there is an x-intercept. You have another maximum up there at 5, so you can see another x-intercept right there. So for those of you who said 1, very good, that is correct. So that's the graph of the derivative. The main takeaways are to make sure you look for where the max and minimum values are, because that'll help you find the zeros of the derivative, the x-intercepts of the graph of the derivative, and we'll tie those ideas together a lot more in chapter 4, where we talk about applications of it, and also a little bit in 3.4 when we do some physics problems. Any questions on these few examples right here? Do you all want to try one more? All right, let's do another one. Once you think you know the answer, just go ahead and hold up the number of fingers, 1, 2, or 3. James, do you have a question? Just thinking? Okay. Okay. So go ahead and turn to your neighbor and ask them what they think, 1, 2, or 3. And then if you're not sure, maybe help them out. So the answer to this one is 2. How many got it? Awesome. If your friend or neighbor got it, give them a little fist pumper or something like, good job. Feels good, right? Again, let me just provide one more explanation, because again, this idea will show up many more times later in the semester, so I just wanted to make sure it's mastered, or at least the foundations are settled. So again, I'm looking for wherever there's maximum or minimums of the original function. So you can see right here at -4, about at -1, and about at 4 are the max or mins. In the graph of the derivative, those will show up as x-intercepts. So you can see right there, those are the 3 x-intercepts. When the graph is decreasing at the same x values, I expect the graph of the derivative to be in a negative quadrant, either 3 or 4. So you can see right here, from like -7 to -4 is decreasing, and you can see that is where the graph of the derivative is in a negative quadrant. And then same principles right here, from -4 to about -1 is increasing, and you can see where we have the positive quadrants, namely the graph is in second quadrant. Any questions on that? Anything I could further clarify? So again, kind of hold on to these ideas, but also, again, just a preview of things to come. Notice that in the derivative, there's max and minimums of the derivative as well. So we want to think, what does that mean? And that's something we're going to explore a little bit more in 3.4, but also in 3.3 in terms of something known as higher order derivatives, and then we'll see what it means in applications a little bit more probably in the next class or two. So going back to the notes, you can see at the bottom, there's the QR code. If you're just looking for something to do while you're waiting for your friends at Toscana, you could go ahead and scan that QR code right now if you want, and you can play that little game just to make sure it's mastered. But again, problems like that will probably show up more or less in every single test up until the end. That's just kind of the context is going to change a little bit. So again, there's the URL. I just found that little web applet there that's helpful just to kind of get you practicing. But if we want to look at this right here, we do have some specific functions that are that we want to look at. So if we look at 4, 5, 6, and 7, again we have the graph of the original over here, and then over here we have derivatives. But of course they're not lined up, so we want to go ahead and just take a moment and say, we have this function right here. Number 4 is what type of function do we have in number 4? Just shout it out if you know it. Quadratic. So go ahead and pair up with your neighbor again, just to kind of work on it together, and look at these 4 original functions and match it up to either A, B, C, or D. So there's a few things to observe. That's pretty interesting. And that's a few patterns that we'll want to hold on. So go ahead and say hi to your neighbor again, and let me give you about a minute to go ahead and work through these 4 while I take a time.
Yeah, me either. One's on the left of the regular. But the derivative is like my understanding from the one you did online, so like whoever has the maximum function there, and the derivative, I don't know, should be like on the axis. So, I guess.
All right, let's go ahead and come back together. I'm going to go ahead and pose this question to the class. When you think, once I'm done with a question, I'll kind of give a quick countdown, and then just let me know what you think. It allows me to get a general feel based off of the kind of the various answers I hear. So number 4, the question is, which of these represents the derivative, A, B, C, or D? What do you all say? 1, 2, 3? I heard B, and that was unanimous. It sounded like it. That is correct. If you look at this, when we look at a quadratic function, its derivative is b. And what type of function do we have here in the case of b? It is a linear function. So this should actually be consistent with what we thought about last week. If you think about the derivative with respect to x of x squared, remember that the 2 comes down in front, and then we reduce the power by 1. So we learned last class that the derivative of x squared, the quadratic function right there, in the first scenario is 2x. And you can see, again, this is a little bit steeper than the identity function. And indeed, this is the function 2x. So that's consistent with the power rule. Okay, let's look at number 3. In number 3, we have what type of function? Cubic. And then what is the associated derivative? What do you all say? 1, 2, 3? That is correct. If you look at this, the derivative of a cubic ends us with a quadratic, and that is consistent with the power rule that we learned about last time. In the case of 6, we have a function that is not a polynomial. Anyone think they recall what function we're looking at right here? Cosine, yeah. So right here, we have the graph of cosine of x. And then, well, we're left with C and D. What do you all say is the derivative, or the graph of the derivative for cosine of x? D is correct. The answer is D. So if we look at this one right here, well, we have another trig function. So that's going to be kind of nice to hold on to, that the derivative of a trig function, of a periodic function, is it always another periodic function? It's not. But the derivative of cosine of x is this one in the bottom right. Does anyone know what function this one is right down here? It is a sine function, and more specifically, it's the negative sine function, because sin is negative. And then, of course, that leaves us with the last one right here. We have a quartic function. Let's change it up. So this is a quartic function. And then when you take its derivative, it's going to give you a cubic function right there. So again, just having some actual context about, like, these are specific functions we know, there's the derivatives. You see the power rule in play in the scenario of 4, 5, and 7. And you see in 6, the derivative of cosine is minus sine. More on those derivatives when we get to section 3.5. Any questions on anything right there? All right, so maybe, hey, just one more thing I want to add to this page right here. Let's go ahead and consider, let me draw one more function up here. It's kind of a little bit of review from last class. So let's consider the function that just goes diagonally through the origin with slope 1. So slope 1, so this is your identity function. So if we were to consider the derivative of the identity function, we would end up with another function. Does anyone remember what is the derivative of x? It's the constant function, and more specifically, what constant function? What constant? 1. So again, we have, this is the slope of this line is 1. So when you consider the derivative right here, f prime of x is going to be equal to 1. If you were to take the derivative of 1, that's when you would get 0. Again, we'll review that again. Maybe one other review problem, just kind of box it off here in the corner. Remember, the derivative of the constant function 1 is 0. And then this one right here, the derivative of x is 1. So again, you want to have the graphs of the derivatives kind of in your back of your mind. We're going to pull them up in various applications. But any other questions about what we talked about on these last 2 pages? All right, some other thoughts about the derivative before we go back to section 3.3. Just like we have one-sided limits, we have one-sided derivatives. We won't use these a whole lot in terms of, like, you're not going to necessarily need to consider one-sided derivatives that much, because most of the functions we work with have an infinite domain. But the similar idea exists that if you have matching one-sided derivatives, then you can go ahead and talk about the two-sided derivative, which is the standard one we've been talking about. But let's go ahead and just look at this little example down here below, and I do want to go ahead and grab something. I should say I want to point something out, and that is a hint of what we're talking about, a little seed I'm sowing there. So we have the absolute value function. Let's go ahead and sketch the graph of the absolute value function just to have it for reference. The absolute value function is the V-shaped graph that goes right there through the origin. So let's go ahead and get that right at the origin. So there's the absolute value of x. So if we consider the left-hand side of this function, so let's go ahead and just highlight that in red, this is negative x. So you could think basically, if we're looking at, let's see what it says. Okay, so this is what we want to kind of figure out. It's differentiable on the left-hand side right here from negative infinity to 0, and also the right-hand side from 0 to infinity, but it's claiming that it has no derivative, but it has no derivative at x equal to 0. So why is that? Because let's think about this. If you were to consider tangent lines on the left-hand side, again, it's going to be a linear function, so that every tangent line is going to just be the same thing. Every tangent line is going to be going down. So if you consider the left of 0's derivative, what that is the derivative of negative x, which is minus 1. Does everyone agree that the derivative of the left side of the absolute value function is negative 1? It's just the negative x is that piece of the function. And then the right-hand side is just going to be positive x, so it's going to be right of 0's derivative, and again, 0 kind of being where there's that point. Notice that the derivative of that side is going to be 1. So those differ. So because the two sides have different derivatives, and if we look at this, there's no smoothness that allows you to transition between them. Because if we think about it as everything's been about limits, and it's approaching. But if you look at this, regardless of how close I get, this will always be negative 1. This one will always be positive 1, and there's no smoothness to cause a nice transition. So what we look at right here is right here at 0. So we can see we have a sharp turn at x equal to 0. So absolute value of x does not have a derivative at x equal to 0. And I'll say this on a blank on the next page, but the derivative is really a measure of smoothness, a nice transition. When there's something abrupt like this, unfortunately, the derivative does not capture those minimums because they were a shock. It's kind of like if you're backing up and all of a sudden you flip your car into forward, your engine is not going to like that. So that's basically what happened there. So there's no way the derivative is going to be able to capture that. Anyone think go ahead and take a moment. Now that I've said that right there, what is the graph of the derivative of the absolute value function? Anyone think they could graph the derivative? So we have the original function. What's the derivative look like?
Would it be like a linear function with the whole at 0?
Yes and no. You answered correctly, but your hand said you were not right. So I saw this. Nope. Grace?
It's one of those functions that doesn't have any point at 0, but it's at 1 and then negative 1 goes in opposite direction.
Yeah, so let me erase this. So you're both right as they are linear functions. Maybe more specifically, I should say it's a constant function. And you both got the idea that it is not defined at 0. This is the function right here. This is negative 1, this is positive 1. So right there in green is the derivative which is x over the absolute value of x. To actually go ahead and find that derivative algebraically, we won't be able to do so until section 3.6 when we learn about the chain rule. But if you just look at the derivative on the left-hand side, notice the slope was -1, so you can see that right there, or that was the function. And you can see right here the derivative of x is +1, so it goes to the right. I really do like calculus because all the ideas really do come together in multiple different forms, and it does take some time to put these ideas together. I encourage you to always think about things that we talk about from different angles. No trig pun intended, I promise. Any questions on that example right there? Yeah, Justin.
I'm sorry, I feel like I always have questions.
Go for it. I like questions.
So would this same rule, would this apply to all absolute value functions? Like when there's an intersection, would there be no derivative at that point of intercept?
Yeah, so let's look at some more general scenarios and the next few pages. So basically, we do want to have in mind, like, where does the derivative not exist graphically? I think that's what you're asking right there. So good lead-in. I appreciate that. So the first scenario we have are corners. So a corner is where the one-sided derivatives differ. Because if you look at this from the left, if we draw these secants getting closer and closer, you can see for Q that we get this line. But if for Q from the right-hand side, as we draw the secants closer and closer, we get this tangent line. This is the exact same scenario that where we had an absolute value. This is just more general. Whenever you have a corner or a sharp turn, the derivative does not exist there. This is probably the most common one we'll see in calculus. It's just easily described in terms of piecewise functions. We have the absolute value as something concrete for it. Another scenario is in this scenario where we have a cusp. So you can imagine this could be like two quadratic functions, like we have some sort of quadratic function, two pieces, something like that. Notice that in this scenario, the tangent lines are equal, but it's vertical. And what do we know about the slope of a vertical line? It is undefined. So remember here, notice that the m of the m of the tangent here is undefined. So, and again, the derivative being the slope of the function or the slope of the tangent line is, if it's undefined, you can't just talk about a function. What it is undefined. We have the other few scenarios down here occurring where there's, in general, wherever there's a vertical tangent, basically where something took like a drastic jump. Won't run into these too much, but again, just kind of the idea of a vertical tangent. Discontinuity, you can see right here, because there's a jump, the tangent lines are different, the red tangent lines. Or if there's some sort of hole, that's also another issue with derivatives. So what that would look like in the graph of the derivative is, as we saw in this last page, just kind of an open dot right up here. Notice that there's no, you can't plug 0 in. 0 is not part of the domain. So that's kind of what it would look like. Mentioned this earlier. The differentiability describes basically the smoothness. So guys, if a lady's talking to you and they're saying, it's like, man, you're like just like the derivative, you could take it as a compliment because they think you're smooth. No? Okay. There is a theorem right here. A theorem, again, is just as a property that's been proven to hold true, that if you have the derivative, you also know it's continuous. So if you start with something and you're like, hey, this is I have the derivative, I can plug in some value into the derivative and it works, I also know that it's continuous there. So, but the question is the reverse. If you know a function is continuous, is it necessarily a derivative? Does it necessarily have a derivative there? No, the absolute value is a perfect example. So I'll say the converse is false. So that is to say, the converse is if continuous, then differentiable. Notice that this is false. because if you consider the absolute value function, the absolute value is continuous at 0, but not differentiable at 0 because of the sharp turn. And that's what we said on this next page. This is kind of a preview of something that we would talk more about in Calculus 2. In Calculus 2, you learn about continuous, or you look at infinity, series and sequences and things like that. So you can see these 3 dots right here. That just means that this function is going to have terms that keep going on forever and ever based off of a certain pattern. So it's an interesting question in Calc 2. If something goes on forever, does it converge to something that's finite? So if something continues on forever, does it basically converge to something that's finite? And it's tough questions. It makes Calculus 2 a very tough subject, but I think it's something to think about that we run into that's maybe a little bit easier for Christians to understand because we have an infinite God and we are finite here on this earth, and we still find ways to understand God through his word, through faith, and through community. So I really think Calculus 2 is an interesting subject because you look at things that are infinite and try to wrap our minds around it, and our minds really only understand something that's finite. But this example right here is something, does anyone heard of anything known as a fractal? So you can imagine a fractal. An example is something like a snowflake. So if you were to just type it in, they're actually really pretty. So let me just throw it in here. Let's see if the internet's working. A fractal is essentially a pattern that if you zoom into any part of it, you will find that same pattern. So you have things like a snowflake right here. You can see right here, if you were to zoom into a snowflake, you will find basically a repeating pattern within that snowflake. So these are known as fractals. I only have seen something like that. I think you've kind of seen it in maybe just some art. On the left, we had something known as the Mandelbrot set, but these are fractals. And this function right here is interesting if it shows back up for us. Because if you were to zoom in to any part of it, you basically find the original function, the original graph right here. So this is a little bit weird, but is a function that is continuous everywhere, but differentiable nowhere. That is literally saying every time you try to plug in a point right there is going to be taking a sharp turn. So there's a little bit of a weird idea that's not intuitive. How can something be completely continuous, but at the same time be taking sharp turns at every single moment? Anyway, that's an idea we explore more in Calculus 2. But that is just kind of the basic idea of the derivatives of graph. Does anyone have any questions on that one? All right, so what I want to do in the last 10 minutes of class today is jump back to 3.3 and get 1 or 2 more rules back in here. But yeah, question, what's up? You won't have to differentiate anything, but make sure you have the basic ideas of things like sharp turns or where the derivative is undefined and things like that. It's just kind of an interesting example that, I don't know, kind of blows your mind. It's something that's Weierstrass function.